Okay. What we're going to try to do today is something I mentioned last time, and that is we're going to study the Stardust mission and what it found. It's pretty important in my opinion, and it's going to lead us to start thinking about the stars in distant star systems. But before we get to the Stardust mission and so forth, let's take a look at what we did last time, in case your brain is as unused to UCF as mine is. I had to really think about just coming up to campus today. I had a really nice vacation. Last time we talked about deep impact. Here's a set of photos, one of the set of photos we looked at. They sent basically a big washing machine-sized bullet into the side of this comet, Nucleus Temple 1. And then they studied the smithereens and the crater, of course, afterwards. It also flew by another comet, actually several other comets. Hartley 2 is the one that they decided on, and what to do that, they used the Earth in the the planetary flyby, the slingshot, the gravitational slingshot maneuver that they've started using a lot for the probes, the spacecraft that they sent around the solar system. It's a nice way to get some free energy if you have the time. And can maneuver it into a flyby. It saves a lot of rocket fuel. So now the Deep Impact mission is officially toast. They lost contact. I mean, it was still pretty good. I mean, it was good up until about 2013, but they eventually lost contact with it then. They think that its computers are stuck in a reboot mode for some reason related to the year 2000. Now you guys, most of you were shrimpy little kids, if that, in the year 1999 and leading up to the year 2000. But there was this big computer panic, it was almost like a cult, that all the computers in the world in the year 2000 were going to fry because Bill Gates set up his dating system to only incorporate what was it, two years or 2 digits for the date. Now, right now, when you fill out forms on the internet and they ask for your birth date, they usually give you 4 numbers to type in. But back then, they could only go up to 99, and as soon as it went to 00, they thought everything was going to go berserk. It didn't really go berserk, but anyways, they think something like that's happened to this one. The other thing we talked about last time was SMOW, which is shorthand for Standard Mean Ocean Water of Earth. And it is the standard that we use when we're studying the relative abundances of hydrogen and oxygen isotopes for anything that we find. So, we have had oceanographers sampling ocean water, up at the surface, down in the briny deep, and, all over the globe. And the abundances that they find are for oxygen 18, relative to oxygen 16, 2005.20 parts per million. ppm means parts per million. All right, and then for the other isotope, oxygen 17, a little bit more scarce, 379.9 parts per million. And everything else, so that's, a very small fraction. I mean, both of those together don't even add up to 1 million. So most of the oxygen in water on Earth anyways is good old oxygen 16, 8 protons, 8 neutrons. So we talked about this, and the idea is that you find a meteorite, or you bring back a sample of the moon. You bring back a moon rock, and you send it to the lab, and they analyze the oxygen and hydrogen in it, and any other element that they want, and then they try to make deductions from that. So this table here, these are the relative abundances. A scientist, the reason that we use SMOW is that we like to compare relative abundances of a meteorite, a moon rock, a piece of Mars, or anything else with what we have on Earth, so that we can kind of make deductions from it about the physics, the history, everything, as much as we can anyway. Sometimes you don't get much of a clue, but a lot of times you do. And actually, that's the lesson of today's lecture, that there's an enormous finding that we've have taken from the Stardust mission in terms of the ratios of oxygen 17 and oxygen 18. Now, there's other sources for carbon. Carbon isotopes like carbon-13 and stuff, for radiocarbon dating and all that stuff. Carbon has abundances as well. Now, they don't use mean ocean water for that. They use this limestone formation up in South Carolina. It's called the PD. Anybody from up there? From that part of South Carolina? Apparently there's a river called the PD River. And it goes through a big limestone formation. So this map here, let me get my cursor over here. This small upper image here is the entire state of South Carolina. And then the crosshatched river, or the crosshatched portion here in the small image, corresponds to this big blob down here. So this is a bunch of, Myrtle Beach is here. So the PD River is this basin, this part of South Carolina. And supposedly they've studied that limestone really, really well, and that's what they use for carbon. And so there's other sources that they use for other elements and stuff. And these are just two of them. And we're going to mostly talk about SMOW with oxygen, but actually SMOW also behooves study for hydrogen isotopes. And actually, I'll talk a little bit about hydrogen isotopes as well. So the isotopes of hydrogen being hydrogen, regular hydrogen, one proton, one electron. Deuterium, a proton and a neutron in the nucleus, and then an electron. And then tritium, two neutrons plus a proton in the nucleus and one electron. So now I have a clicker item about SMOW, and I want you to really think about this one. See if I can start this question. I want you to read carefully and think, because this is an upper level thinking task. All right. Go ahead and answer. But read first and then make a decision about. And you guys, I would jot down this table. Make sure it's somewhere in your notes. Put a couple stars next to it. We're going to be talking about it through the wazoo this week and probably between now and April. Also write down this question, because this is a good question that you might find helpful to have studied when you get to the next exam and when you get to the final. And I'll just give you a hint. You may have already twigged to this. I put an awful lot of store in this entire course to this particular topic, because it unites the solar system with the rest of the galaxy. Okay, this is our stepping stone. All right, I see a bunch of you have answered. This is interesting. Good. This seems to be different up here now. Okay, 10 seconds to vote. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Okay, pretty good. All right. Jenny usually does this. Let me switch over to the computer. Here's the result. Okay, and it looks like a bunch of you selected B and C. Nobody has a clear majority. There's a little bit of A and a little bit of D in this. So let's go back to the regular slides here. B is actually the correct answer. Now let me give you the reason for that, and I'm glad that more of you chose B than chose the other ones. But if you didn't, here's why. What you want to do, notice that there's a word therefore. Whenever you see the word therefore, that means you're making a decision, or you're making some kind of a logical, not a logical assumption, but a logical outcome based on the words previous to that. So the words previous to that are 2022.33 parts per million, all right? So therefore, your deduction is that it's actually enriched. And the reason for that is it's got more than 2005. All right? So that's a good way to think about it. So if you got this one wrong, jot that down in your notes. That number, parts per million, how many parts per million? If you've got a lot of them, you might even have 3,000 parts per million or more. It just depends on what you're studying. And here's another thing. The water inside a nuclear reactor, that they use for cooling, I'll bet those things are loaded with 18s and 17s relative to SMOW. Now, I want you to make a note of a few of you tripped up on that, 12%. 2022.33, that's a ratio. So it's not, what it is, it's parts per million. So you could think about it as 2.02233 times 10 to the minus 3 times the oxygen. So it's saying it's 2,000 times more and you don't really say that in relation to SMOW anyway. So A is a misuse or a misreading of that term. Less oxygen, option C, is incorrect because the number itself is bigger than what the table is. So you're over here on the table. Here's SMOW, all right, in the very middle block. And then here's your immediate, so this is like saying, all right, matter of fact, I'll try to actually put 2022.33 in this before I upload to YouTube. But anyway, so here's your meteorite over here at 2022.33, and that is bigger than this. So you can't say that it's got less oxygen. All right. Now, some of you, go ahead and make a note of option D. All right. And option D is actually an important, it's wrong. But it's wrong for, what's wrong with it is important. And the option D says, all right, if you've got enriched, it's like saying, okay, I'm enriched in oxygen 18, so I'm also going to be enriched in oxygen 17. And that is wrong. Make a note of that. If you have an enriched substance in oxygen 18, you might have depletion of oxygen 17. You might have even higher enrichment in oxygen 17. It just depends, because there's all kinds of physical and nuclear processes that will change that abundance. And that's why we test. And we test the ratios, we look for patterns, and then we try to figure out, all right, so this means that, this asteroid or this comet formed, so many astronomical units out in the Oort cloud or where, the Kuiper belt or wherever it happened to form. You make decisions like that based on your abundances, on your isotope ratios. But they might be different. Oxygen 17, they might not both be enriched. One might be enriched, one might be depleted. It could be vice versa. It just depends. And that's why, as they say, that's why you play the game. That's why you make the measurements, to see what the numbers tell you. And in this situation, you let the numbers do the talking. And then you try to figure out what the numbers are telling you. All right? And we got a lot of numbers from the Stardust spacecraft. Now, there's a lot of background information on Stardust, and Stardust-related concepts in Chapter 13 and Chapter 14. All right? And Chapter 14 has some explicit mentions of the Stardust mission. It's just a little table in chapter 13, but concepts in both chapters will help you understand this entire Stardust mission. Now you can see that yellow arrow that I've got up there right here, and this little thing, it looks kind of like a tennis racket. That is our capture device, because this spacecraft was sent into space for the express and only purpose of catching stuff from this comet, Wild 2, and bringing it back in that tennis racket-shaped object to Earth for study. Now, we haven't, we've got moon rocks, and we've actually got some Mars rocks that have fallen to Earth as meteorites, but we've never brought anything back, or at that time, we had not brought anything back from a comet. We'd sent spacecraft out to look at comets, and we look at them through telescopes out the wazoo. All right? But actually bringing back something from the halo, or the, I shouldn't say halo, the coma, the tail of the comet. No, we haven't done that. Now, I want you to jot this down. It's a technical article, but you can look at the figures in it. It's written by a guy named Kevin McKeegan and a bunch of other authors, so that's what et al. Means. Kevin D. McKeegan and friends. Science, from the journal Science in the year 2006. And this was it's 12 years old now, but it's still really important. And you can jot down those numbers and, and find it. And the McKeegan article is explicitly designed, or is explicitly written to analyze or to describe the oxygen isotope and the hydrogen isotope ratios that they found from the stuff that came back in this. Here's a close-up of the tennis racket. All right? Now you can't really tell how big the tennis racket is. This is at ground control in Houston, where they're putting it together, or maybe it's out at the Cape. Wherever they're putting it together, this is the tennis racket thing. All right? And what they're going to do is they're going to try to fly it through the coma of Wild 2. Right, now, Wild 2 is this image on the right. Now, that's a photo of it. And here's a couple other ones, Borelli and Temple 1. Temple 1's the one that got the dishwasher treatment. bang, bow. A little bit before Stardust. Stardust flew through the coma, and with the tennis racket exposed, and then it was designed to come back towards Earth, jettison the capsule containing the tennis racket, and then parachute back down to Earth, and then hopefully successfully without getting all blown apart, because some of the other sample return missions have failed spectacularly. They've gotten some stuff out of them, but so that's the basic idea. Now I want to give you a blurb here from chapter 13.3. This is about the stuff that's in the coma, in the tail of a comet, the bright part that glows. Okay, beyond the asteroid belt where comets spend most of their time, the ices in a comet are frozen, solidly frozen. But as a comet approaches the sun, it begins to warm up. And if water, H2O, is the dominant ice, significant quantities begin to vaporize as the sunlight heats the surface above 200 Kelvin. All right, now 200 Kelvin, the freezing point of water is 273 Kelvin, right? So as you get above that, at 200 Kelvin, it's not going to melt. But I was just up in Michigan and Ohio, and it was kind of interesting, for my spring break. And it was kind of interesting because there was snow on the ground up there, and we got snow while I was up there. And it was interesting because they'd gotten, these big snowstorms that were hitting, like Boston and New York and Virginia and stuff, last 3 weeks. The backside of it was so big, it's like a hurricane. The backside of the storm system was dumping snow in Toledo and Detroit and even Chicago, I think. All right, and when we got up there, it was days after the storm, but there was still snow on the ground. But it was only on the north slopes of hills, and the south-facing slopes of hills, it was already gone. Now the temperature was below 32 for most of the time that we were up there. We were freezing our you-know-what off. All right, so it wasn't melting. It was getting solar radiation on the south-facing side of a hill and evaporating. And that's what this is talking about. You might not be above the melting point. That's all right. Solar radiation will cause it to evaporate. All right? And we get that, that's how we get rain. The rain that we got last night that was so stormy, that could have evaporated, who knows, over the Indian Ocean, 2 weeks ago from solar radiation. Or somewhere over the Pacific, 4 days ago. By solar radiation. And then it gets up in the atmosphere and then eventually cools off and it falls as rain. So that's what the coma, the tail and the coma of a comet are dominantly about. But let me just add one comment here. Stardust, it wasn't really looking for H2O. It was looking for other stuff. Right? So this is what chapter 13.3 says, and make a note to yourself here. Stardust was looking for other stuff in the coma of Comet Wild 2. Now here's a picture of silica aerogel. It looks like a piece of frozen air. It's actually silicon and some resin and stuff. And I don't know how they make it, but it's extremely light. It's a really good insulator. I mean, you can see this chunk of it, it's just bounced on this person's fingertips, like it's, what that reminds me of? Those things that people eat from the grocery store, rice cakes, they don't have any flavor, but people eat them, but they're really light. Ramen noodles, really light, I'm sure everybody here knows about ramen noodles. Anyway, so this is really light stuff. It's very light. So it's nice to put in a, if you can use it for something in a spacecraft. It doesn't add a lot of weight, so that's good. It's a really good insulator. Now check this picture out. Make a note. Silicon aerogel is a good insulator. That's a stinking blowtorch down there. And look at those little crayons. They don't care. They're not getting any heat. The heat's not transporting up, not very rapidly. I mean, if you keep it going there for several minutes, I'm sure eventually they'll start to get melty. But yeah, it's a good insulator. All right, so it's an amazing substance, silicon aerogel. Good insulator. And what they were trying to do was get those particles of stardust from the coma of Wild 2 embedded in the aerogel. And they did, they brought it back. Now here's clean room in Houston. And you can't see it in this picture, but it's kind of hard to, here's another picture. There's the tennis racket, but this one, it's hard to see how big the tennis racket is. But in this, so look at this picture. Here's a picture of a guy. There's his thumb up here. So this is, each of those little blocks in the tennis racket is maybe the size like a candy bar or something, or a couple Snickers. It looks a little bit slightly different shape. So each of these, oh, there it is. There's the tennis racket. Okay, so you can see that those aerogels are about the size maybe of a couple Snickers bars, or maybe, yeah, like a couple Snickers bars, or maybe couple Halloween-sized Snickers bars. All right. So there's the, so it's not very big. It's amazing. We put it on this huge rocket. Tons of rocket fuel. Fancy spacecraft. Just to get this little old tennis racket into the downwind side, the lee side of a comet. Fly it through there, get that stuff embedded in there. Here's a track. We did. We got stuff in there. You know what it's, the other thing it's like, if you ever watch CSI or some detective mystery on TV, and a lot of times they'll have a weapon that they have to check the ballistics, so they shoot it into a water tank, all right, and then they recover the bullet, because the water tank will stop it without causing the bullet to fracture. Okay, so they find the murder weapon, they fire it, then they match it up and all that kind of stuff. Same thing here. So this stuff, the idea is that the silica aerogel, that's it. Capture. Got it. So then what they do is they get a microscope and they try to get all the, you can see, in fact, it looks like a photograph of the smithereens after, like in a movie, the hand grenade goes off, or Wolverine blows something up and then walks away from it. And, the smithereens go up on diagonals in all directions. But these ones, the impact threw fragments out on various diagonals and stopped them. And then we brought it back to Earth. All right. So what they do is they go out to the end of each of those little tracks and they see what they can see. And we have seen quite a few things. Now, here's one of the things that they put it in. This is the center image. That's actually an X-ray diffraction image. And so it's black and white. It doesn't have colors with it. But looking at that, the patterns of those diffraction lines, and these are circular because it's through a circular aperture. You're not looking through a slit. Like what we did in class. We did that, didn't we? The diffraction lines, first day of class? Yeah. Okay, that was vertical slits. And so, but in this machine where they were looking at stuff, it had a circular opening. All right, so this is X-ray diffraction, and there's an article by Westphal et al., and I don't have the citation for it, but it's in the same issue as the McKeegan article. And so what they did is they said, all right, well, what we got here is we got some iron, calcium, chromium, and magnesium or manganese ions, and it's color-coded. So over here, and look at the size down here in image A. 1 mu meter, that's a Greek letter mu, lowercase mu, and that means micro. Right? So this is 1/1,000,000th of a meter, right? This line segment here. So this is a really tiny fraction. All right, your hair, a hair from your coconut is less than a millimeter, so it's a fraction of a millimeter. Okay, this is a 1,000th fraction of a millimeter. A millimeter is a 1,000th of a meter, and a 1,000th of a millimeter is a micrometer, and that's the length of this line here. So this is a pretty. So they look at it, and then they look at this diffraction pattern, and they say, all right, we got a lot of. Let's see, right down here, this purpley stuff is chromium and manganese, and then right in here they got a lot of calcium. That's the greeny. And then over here, oh, we got some iron over here at this end of this fragment. This very small fragment. Can you imagine that? You know, gram for gram, what they brought back, I wonder if anybody's ever calculated that. You know, the amount of payload that they brought back has got to be measured in grams if it's even a single gram. Maybe not even a single gram. All those millions of dollars to bring back a gram maybe of this stuff, it's incredible. Now, over here on the right side, what they're looking at are minerals. All right, so over here, they're looking at this thing, and guess what these minerals are? Spinel, that's this red, you know, these two red parts up here, and then green, olivine. Spinel, that is a very common mineral in our planet. It is considered a gemstone, all right? And you can get a ring with a nice quality spinel. I think it's actually a birthstone, if I'm not mistaken. All right, now, and it is very common in the crust and the mantle of Earth. Same with olivine. Olivine is more, as you might expect by the name, it's more of a greenish mineral, all right? And these are not pyroxenes or anything, but they find pyroxenes in all these things as well, right? Pyroxene is, you know, the famous pyroxene I love to think about and talk about that we find in space, and we find, you know, there's all kinds of pyroxene minerals. And the most famous one, in my opinion, on Earth is jade. You know, the jade gemstone, beautiful jade, is actually a pyroxene. And spinel's another one. What is another one? Garnet, G-A-R-N-E-T, garnet. And that one is a birthstone. I believe it's January. Okay. Anyway, so they can look at these diffraction patterns like this in the center and say, all right, this pattern, this part of the pattern, that shows calcium and magnesium. And this part of the pattern over here shows iron and calcium. And, you know, so they figured out, they do these false color images, and that tells them stuff. You know, like, because, and here's why. And you can make a note of this. You know, the boiling point of the melting point of spinel, the melting point of olivine are different. All right? So if this thing forms with olivine and spinel, then you know that it had a certain temperature at formation. All right? And that tells you something about the history. And you figure out the arrangement of it, and you start to figure out everything that happened. All right, now, here's an isotope ratio diagram from the McKeegan article, right? And you'll be able to look at this one up close. You just log on to UCF has a subscription to Science, so everybody can look at it. And the Stardust samples are here. These are some of the isotope ratios. Now, IDPs and meteoritic IOM, that's a different bunch, okay? And here's something, comets, all right? So the water in comets, and HCN, I think, is cyanide, cyanic acid, HCN. Now, Interstellar, unfortunately this thing, let me try to fix that. Let me get rid of that. Hold on a second. I want to look at this carefully. Let me get my cursor here. All right, so looking at this diagram, now this one is, as I said, this one is hydrogen. And hydrogen is the other element that you base on SMOW. All right. And interstellar molecules. And this gray bar here, it says, all right, this is the terrestrial range. So these samples, these little circles, here's a blob of stuff over here from Stardust. These guys are kind of grouped off to the side. But these other ones, here's one from Stardust right on the terrestrial bar. All right? And this one here, you can see these little sideways lines, the horizontal lines. That's the error bars. There's horizontal error bars. And this one here on the left of the gray bar, up where it says T35, 27, this one over here, that's actually overlapping the gray bars. So that's fair to say, yeah, that's pretty close to terrestrial. But now this stuff over here, definitely, see the error bars here horizontally for these open circles? They don't reach all the way back to the Earth, the gray Earth bar. Right? T13, it's out here a ways too. So what that tells you is these little fragments that they analyzed, they don't look like the same water, the same hydrogen and deuterium ratios that we have on Earth. They're a little different. All right, and so that tells the astronomer and the planetary scientist, you got to figure out the physics of this, because this thing didn't originate exactly the same way that the moon and Earth did. And Mars, Mars has got a little bit different mixture of isotopes than Earth, but not far off. So this is deuterium and hydrogen ratios relative to SMOW. And, SMOW is equal to 1. Right? So if you see 1 here, that means you're exactly right on it. Okay? And so, the terrestrial range is a little bit depleted and a little bit enriched relative to 1, relative to SMOW. But now down here, protosolar H2, that's molecular hydrogen, that's really, really low. All right? D over H, really low. So we would consider that depleted. And up here, comets, these are enriched. So this black thing here for comets, and this one here, this black one for H2O. So the hydrogen in HCN and the hydrogen in H2O for comets right here is enriched relative to SMOW. All right, let's take another look. Now, here's some photographs. Look at this. Everybody look. Put your phone down. Put your phone down and look. Look at what we got. Good. I'll get your eyes up here. Those are bullet holes in the frame that held the tennis racket together. The tennis racket is aluminum square or aluminum rectangles, and you slot the aerogel in there. These are bullet holes in that. Okay? And so these ones these are the experimental ones up here, and then these bottom 4 are observed on the Stardust sample return. All right. And so you can see that stuff plows into the spacecraft, and even those aluminum bars, the aluminum framework, you know, you can get stuff off of that. You bring that back, it'll collect as well. They were, you know, trying to get a lot of aerogel collection, and they did. But even some of this stuff that blew a hole in the side of it. Now let's look at this one. My wonderful students, write this down. McKeegan et al. Figure 3. McKeegan et al. Figure 3. All right. Now here's a bullet hole. And you had something blaze through there. All right. Some kind of a fragment. This is an electron microscope image. All right, now you can't make a note of this, but you can make a note. Figure 3, McKeegan et al. All right, you can go look it up on the internet. Electron microscope image. Very nice. They could even see this little residue down here. See this little nugget? Look at this, 100 microns. Okay, so that's 1/10 of a millimeter. All right? So this is maybe on the order of size of a human hair. So they're looking at this little nugget here. Right, so they're happy. Yeah, we'll analyze that baby. You know, you plow through the aluminum, or you know, maybe it was titanium. I don't know. You can look it up, I'm sure. Yeah, we got this bullet hole. Hey, there's a little nugget of less stuff left. So this is like, when in CSI, they always put paper bags on the victim's hands so they can see if they have gunshot residue. Okay, that's gunshot residue. All right. So they're going to analyze that. Now here's a close-up over here. Now we're down to 10 microns. All right, so this is 10 times magnified. So that's looking at this baby right here. All right, and you can see that this is a slightly different angle. So they're looking at this. And then they're focusing in, oh, wait a minute, we got something here. They're looking at, see this little yellow, everybody look, come on, look at that yellow circle. Now we're getting down to the nitty gritty. This is about a micron maybe a little less. Now, here it is. This is a photograph, false color image I should say, of that nugget. The color code, look at this up here, delta 17 oxygen. All right. Now what this shows you is the higher that number, delta 17 oxygen, and I'll show you how to calculate that on Thursday. You're going to be doing some calculations with that. And delta 18 oxygen. The higher that number is, the more enriched in oxygen 17. So this is the numeric way of saying how enriched something is relative to SMOW. All right. So red. Come on, cursor. There we go. So red up here is 800 delta. So that means 18. That means 800. Relatively high number. Here, 0 means exact same as SMOW. Right, so make a note of it. In this part of McKeegan's figure 3, this is image C. That the red means enriched, 0 means same as, and dark blue means depleted for oxygen 17. So anywhere you see a blue, you don't really see any blues on this image C. It's false color image. But you see some greens and a little bit of light blue. So that's a little bit depleted, except for one place. Right here. Look at that. That is H-O-T. Right there. All right. That is the hot spot. And what that signifies is in this nugget, there's one teeny little hot. So this is loaded. It's up there in the reds. It's loaded with oxygen-17. And you may be saying to yourself, Dr. B, why are you getting all worked up about oxygen-17? Boring. Not. Because look at this quote at the bottom of the screen. This is the money quote. The isotopic composition is typical for this hot spot, is typical for pre-solar oxide and silicate grains belonging to group 1. Now I'll tell you about group 1 in a few weeks. Group 1 is thought to originate in red giant or asymptotic red giant branch stars. So that little hot spot is from another star system. And that star is no longer around. That star has already gone into supernova and is verschwunden. It's disappeared. It's gone. But we see plenty of red giant stars. You know, when we look out into the universe, and you guys have Betelgeuse. Make a note. Betelgeuse, constellation Orion, is a red giant star. And by God, we bagged one from the back end of a comet. And that tells us that our solar system used to be in the guts of a red giant star. At least part of it anyways. And that little hot spot there, little teeny, less than a micron, less than a millionth of a meter, is a part, undisturbed, unchanged, for billions of years, who knows how many billions of years, unchanged from a red giant star. Somewhere where we used, nearby us in our part of the galaxy. And that, my wonderful students, it's wonderful. This is the first time that we have found and that is why this particular article is so important. We have had this theory that the solar system formed from the smithereens of blown up supernovas. This is the proof of it. We got it. We were right. Now, we can't tell from this one exactly where it came from, but we see this isotope ratio in all kinds of red giant stars. Now we got one. So this is not from the lab. You can make you can load up oxygen-17 in the lab. You've got a nuclear reactor, lots of neutrons floating around. Bing! You can load up as many as you want. For this one, there's no nuclear reactor on Comet Wild 2. The nuclear reactor was a red giant star 5 billion years ago. Oh my goodness. My wonderful students, this is it. McKeegan et al. All right, it's 10:06. I'm going to dismiss. And on Thursday, bring thy calculators. We're going to calculate at the wazoo. All right, you're dismissed. I'll see you on Thursday.